Hey, Mr. Allred here, and we're going to do what is known as the transformation of graphs. So basically we just talked about parent function graphs, and we know the general shape of certain functions. So what we're going to do is look at how making adjustments to those equations will change their graph. So I'm going to make a couple of examples here and try and go through detail, but the rules are summarized in a separate file. But first of all, we say that if we know the graph of f of x, sorry, we're on the wrong slide. If we know the graph of f of x, then negative f of x will reflect around the x-axis. So let me see if I can explain that. So let's use the square function, since it's our most basic one, and we know that is f of x equals x squared, and the kind of graphing basis for that is we take a couple points and we square them, and they all turn out to be positive for x squared, and we have that graph if we put it together the best we can, and it gives us the U shape. So to kind of demonstrate what happens when we do negative x squared, and we can call this a different function, but in this case, whatever we plug in, we're calculating the same value when we square it, but we're actually changing the value afterwards. So we're still plugging in the exact same numbers, but I'll square negative 2 and get 4, but that negative out front, when I change the sign of the function, will actually take it to a negative 4. So this negative in front of the x squared means I get whatever the value was after squaring it, but then changing the sign of it. So in these cases, it's going to turn all of my outputs from the first graph to negative, which, as I just stated, will reflect this over the x-axis. So it looks like an upside down parabola. Okay. So we said this will reflect around the x-axis. So if you see one of our 5 functions, the square function, the square root, the cube root, or absolute value function with a negative in front of the function, and we'll go into more detail so it's clear later on, that means it's going to flip it over or rotate it around the x-axis. Alright, so the next thing we're going to do is, what if we change the input? Okay, so we have f of x, and then we're going to have f of negative x. Well, let's just take one of our other functions here, and let's make it the cube function. So in this case, the cube function, if we plug a couple things in, I won't plug in a whole lot. I'll write out the same table from the parent function graph. Negative 2 gives me negative 8, negative 1 gives me negative 1, 0, 0, 1, 1, 2, 8. And I can't plot all those points, but it'll be good to have them to kind of show what's happening. But I got the general shape of the x cubed. I tried. So when I say f of negative x, that means I'm replacing the x as the input with negative x. Okay, so this negative is inside the function, where the negative in the previous example was outside the function. So when I talked about the previous one, that would have looked like negative x cubed. This looks like negative x quantity cubed. Okay, so that's around the x-axis. This is around the y-axis. But I can show you that from a little chart, because we're taking the number that we plug in and we're changing the sign of it right off the bat. So when we plug negative 2 in, that little negative inside there turns it into a positive 2, and then positive 2 cubed is 8. So really we're changing the sign of everything that we put in, and then it changes the sign of the output. So if we go through here, what we see is that it reflects around the y-axis. That might be a little bit hard to see because of the different types of ways x cubed behaves, but a negative inside the function takes it around y. A negative outside the function takes it around x. Okay. The next thing I want to do is add a number to the end of a function. So, what function should I use here? Let's use the square root. So let's say we have f of x equals the square root of x. So very quickly, I only do a couple of points here. I do 0, 1, and 4, which gives me back a set of points that I can graph. Also remember that there's a domain restriction with the square root. So the square root of x looks like this. Okay, squirt, if you remember me saying it. So I'm going to add something to the end of it. F of x equals, let me leave that off because I have been. But let me take the square root function and add something to the end of it, like 3. So what does that do? As far as, let me move that over too. Okay. So in this case, I can plug in the same numbers. Square root of 0 is 0, but then I add 3. So I get the point 0, 3. Square root of 1 is 1, but add 3, that gives me 4. 1, 4. Square root of 4 is 2, add 3, that gives me 5. So 4, 5. So look what it did to our graph. As I said up here, okay, if that c is greater than 0, then we shift the graph up. Okay. So then lastly, if we take the same thing, square root of x, and we make c negative, we can make another chart. X and y, we'll plug in the same numbers. And in this case, square root of 0 is 0, but I'm subtracting 3, so it moves it over. This is really changing our y values here. So plug in 1, I'll get negative 2. Plug in 4, I'll get negative 3. So let me see, my face might be in trouble down here, so let's move me over. Oh, I'm sorry, that last one was a mistake. So I'll plug in 4, square root of 4 is 2, and I subtract 3, so I get negative 1. So the points I get are 0, negative 3, 1, negative 2, 4, negative 1. So I still get squirt, but he's been shifted down. So if that c is less than 0, which means negative, then we shift, down. We'll shift it down. Okay. So I'm going to skip slide 4 and come back to it, but slide 5 here. We're also adding a constant, but notice we're adding it inside the function. So this is f of x plus c. So we're changing the input here, not the output. So the difference is it's not x squared plus 2, it's x plus 2 squared. So let's just see. Is that a good one to work with here? Yeah, that's fine here. We'll work with x squared. So we already know what the basic x squared looks like. We've done it enough. And we can graph variations of x squared using intercepts and vertex from previous material, and that's fine. But sometimes you might not want to go through all that if it's a simple change. But what we're going to do here is we're going to say, change it to red. Are you red yet? X plus 3 squared. So we'll make a little table here. plug in x and y. So let me just do a couple things here. Let me do this. Well, I need to do a couple. I'm going to rearrange this. So let me see. Let me do -5, -4, -3, -2, -1, and you'll see why in a moment. So -3 plus, excuse me, -5 plus 3 is -2, and I square that to get 4. If I plug each one of these in, I see that I get the same points I get out of the the old squared function. So I'm plotting these points, and we'll see what happens here is that positive inside the function input shifts it to the left. So in this case, if c is less than 0, then shift, excuse me, greater than 0. I knew what I'm doing, but I wrote it down wrong. If it's greater than 0, then shift left. So opposite direction of the sign. Okay. Over here, if I do x minus 3 squared, I'm going to pick the points that I know will work here. So let me say 5, 4, 3, 2, 1. And this gives me the same thing, 4, 1, 0, 1, 4 when I plug them in. So that's moving it over to the right this time. So once again, it's moving it in the opposite direction. So what we should see here is if c is less than 0, then we shift right. Okay. So keep in mind that if the plus c is on the outside of the function in the previous slide, that moves it up or down. If the plus c is inside the function, under the square root, inside the absolute value, that will shift it left or right. Okay. Let me pause this before I do the last one because I think I may run out of time.